Hello everyone, I am Pawarit Manakul from Thai Tokyo Tech ICTAS program. Today I will present about my mini project of software designed for AI and IoT. First, I'm gonna talk about myself and then I will give you the information of the smartphone sensor. Then I will talk about the reference work. Next, I will talk about the patient walking speed and distance per step, which is my project. And then I will show you the lab script demonstration and give you the conclusion and discussion. So about myself, I am Pawarit Manakul. I graduated from Kasetsart University in Faculty of Electrical Engineering in the telecommunication field. My previous project is about the efficient partial retransmission AIQ strategy with verification-based decoding for non-battery block codes. So for the smartphone sensor, first is the motion sensor. I use two kinds of it. First is the accelerometer, which can detect the acceleration of smartphone. It has MEMS. The concept of it is if the acceleration applied to the mass will move and adjust the capacitor. This situation will convert the capacity to acceleration data. The next sensor is angular velocity sensor. So it uses the same concept as acceleration sensor. If the angular change, the capacity will also change. For the position sensor, we have the GPS or Global Positioning System. That concept that the mobile will communicate with the global network of satellites and use the propagation signal delay to calculate for distance between user and satellite. That they can determine the location and time. The data from the GPS is latitude, longitude, and timestamp. The drawback of this system is that it requires the line of sight, so we should do the demonstration outside the buildings. So for the reference work, I'm studying in the paper titled A Novel Accelerometer-Based Technique for Robust Detection of Walking Direction. And I'm studying with the gate cycle phases, parameter to evaluate and technology. You can follow this reference if you're interested. So for the first paper, they use the accelerometer-based technique. The distance can be estimated in pedestrian dead reckoning. They use the foot-worn accelerometer and use the concept of dominant trend duration. Forward and backward walks with speed variation on a straight path as well as for forward walk at normal speed on a turning path. The results show that 98% detection accuracy is achieved on linear path and 93% on turning path including left and right turns. So for the concept of dominant trend duration, there are distinguished step forward and backward direction. The anterior-posterior acceleration is analyzed during swing phase. A used forward and backward displacement were made without rotation. Major central trend lapsing maximum duration and thus named dominant trend. Acceleration is monitored for dominant trend in either direction during an entire swing phase. The duration of the dominant trend is a normal feature of acceleration and called dominant trend duration, or DTD. So here is the figure about their work. As you can see, the forward pattern is plus and circle and plus and circle. The plus show the high and circle show the low. And for the backward, it's the circle plus circle plus. So the forward is the rising trend between two falling trends, and the opposite order of the trends is witnessed for backward displacement. For data collecting, the tests were performed on a straight path, which forward and backward at 3 self-select speed on straight path. They used slow speed, normal speed, and fast speed. The next they do the right angle turning path and left angle turning path. For the data processing, they use Butterworth low-pass filter and fast Fourier transform to analyze the data. Okay, now we will move to my project. My project is about walking speed and step length. So first we will collect the motion and position data from the user and then visualize the data. Next we will filter the data and calculate force counting step and compare the data of acceleration data and angular velocity data. Then I will calculate for walking speed and step length as a result. So for the first part, the data collecting, I lay down the sensor face down flat in a shoe and then analyze walking pattern. First, when the normal people walk, we put the force at the heel first and then we lay the foot down to the ground. Then we push up, acceleration, and then deceleration. The walking pattern is like a sine wave in this case. The forward walking along the straight path, I make a right turn for 2 times. For the data processing, I use low-pass filter to deal with the noise and visualize and analyze the data. Acceleration data in y-axis can see and count the sine wave clearly. For the angular velocity data, I design x-axis. And for the turning, the angular velocity data in y-axis and z-axis can detect turning. After the analyze, I use thresholding to count the steps. The distance, I calculate the distance between latitude and longitude point to get the total distance. Here we're gonna move to the live skip demonstration. Okay, this is my live script. First, I begin with connect my smartphone to MATLAB using this command. And then I begin collect the data. I also provide the narrator in this step for user. After finish working, I stop locking and collect the data from 3 sensors in the smartphone. Then I plot the original data. As you can see from the Excel Y data, this data is good for counting the step. And for the angular velocity x, it is also good for counting the step. But all the data we get are very noisy, so we have to deal with the noise. I decide to use the low pass filter for filtering the noise. And this is the result in the orange line. As you can see in acceleration sensor in y-axis, we can count this step easily. And for the better, we can use the angular velocity sensor in x-axis. As you can see from the orange line, we can count it by our eye, but we decide to use the thresholding to count this. And then we move to the step counting section. So for the step counting, I decide to use the threshold about the 0.1 for acceleration sensor data in y-axis and 0.2 for the angular velocity sensor data in x-axis. From the Excel AY, we get 42 steps, and for the angular velocity x, we get 45 steps. And for the distance calculation, I use this formula to calculate for the distance, and then I will clear out the data that is less than 1, which is the user didn't move, and then I plot the data again in the geoplot, and then we calculate for the total distance, which is the sum of all the distance. Okay, so then I will show all the result. The result we get is the counting step from angular velocity x is 45, and the total distance is about 49 meters. And then we calculate for the step per second and the distance per second, and so the distance per step or the step length is about 1 meter. You can use this information for the user to compare with the normal step length of the patient with the same height and age. And for the angular velocity y, we can see two peaks here. So it shows that I take a right turn for 2 times in this case, and that is the all of my lab script. So we finished the lab script demonstration part. For the conclusion, the result shows that this program can count the step correctly for angular velocity, and for acceleration data, we have to adjust the threshold to get the correct result and use the proper filter for the data. The next is walking backward have the opposite pattern compared to walking forward pattern. After we get the result, we can use this data for medical and non-medical application. And from the plot, z-axis and y-axis of angular velocity data can be used to detect the turning of walking. As you can see from the angular velocity y, I said that I turn right 2 times, and you can see the peak of the plot. For the discussion, first advantage. In this project, I use only signal processing, so we can use machine learning to enhance this project result and provide more data. You can use machine learning such as classification learner to classify the data labeled as walk forward, walk backward, turn left, and turn right, or study the walk pattern of user, which can be used for user identification. I use these data with duration of direction and distance per step data. All of these will provide date reckoning for indoor positioning, which is better than GPS. For the medical purpose, we can use this data as users' information to evaluate health of patient. For example, why the step duration is too slow. Is the patient has heart disease? Or you can use with the spot. For the drawback of this project, we have to put the device in shoe that may not be convenient. In this case, I use smartphone. For user, if the sensor is very large, the user may not walk normally, and the pattern and detection in this case can be inaccurate. So I prefer the small sensor. The sampling rate is very important because if it's too slow, it cannot detect the change of data. If it's too fast, we have to deal with large data and noise. As you can see from plot, walk path is not clear because I walk between indoor and outdoor. We can conclude that GPS is not very accurate in small area and indoor situation. Moreover, I should collect more data to make this program more reliable. And the walking pattern and DTD can be used to analyze the user more deeply. And that's it. Thank you.